Drop an ice cube into a glass, and it floats. Every time. You hear that familiar clink against the glass, watch it bob at the surface, and never think twice about it. It's one of the most unremarkable things you'll see all day. But look at almost anything else. Melt a candle, and the solid wax sinks back into the melted pool. Cool molten iron, and the solid sinks in it too. Freeze mercury, and the solid sinks in the liquid mercury around it. Nearly every solid is denser than its own liquid. It sinks. Water breaks that rule. Its solid form is lighter than its liquid form. That's backwards. And it's one of the strangest, most important quirks in the physical world. Being less dense doesn't make something float by magic. It comes down to a simple rule of buoyancy. An object floats when it pushes aside a weight of liquid equal to its own weight before it's fully submerged. Something less dense than the liquid around it can do that without going all the way under, so it settles at the surface, part above, part below. Ice floats because, size for size, it's simply lighter than the water it displaces. So why is ice specifically lighter? Look at a single water molecule. It's shaped like a wide V, one oxygen atom, two hydrogen atoms. The oxygen end carries a faint negative charge. The hydrogen end carries a faint positive charge. Opposite charges attract, so each molecule's positive end is pulled toward a neighbor's negative end. That pull is a hydrogen bond. It's weak on its own, but billions of these small pulls happening at once shape almost everything about how water behaves. Cool most liquids down, and they just keep shrinking. Molecules slow, pack closer, density climbs in a straight line all the way to freezing. Water does that too, for a while. Cooling from boiling down toward freezing, ordinary thermal contraction only changes its density by about 4% across that entire range. Then, at about 4 degrees Celsius, something switches. That's the point where water is at its densest, its molecules packed as tightly as they'll get. Cool it past that point, and instead of continuing to shrink, water starts expanding again, almost as much in those last few degrees alone as across all the degrees before it. Here's why. Hydrogen bonds start locking the molecules into a fixed, open frame, a hexagonal lattice. Each molecule bonded to 4 neighbors held apart instead of packed close. That open scaffolding takes up more room than the loosely jumbled liquid it came from. By the time water fully freezes, the solid is about 9% less dense than the liquid it froze from, roughly 917 kilograms in a cubic meter of ice, against 1,000 kilograms in the same volume of water. Picture a jar of loose marbles, then locking those same marbles into a wide, evenly spaced frame. Same marbles, more space between them, more total volume. Ice isn't lighter because it's a different substance. It's lighter because its molecules are held further apart. Here's a neat check on that explanation. Scientists can make water using deuterium, a heavier form of hydrogen, instead of normal hydrogen, what's called heavy water. Heavy water ice is actually denser than normal liquid water, and it sinks. That's not a contradiction, it's confirmation. The extra mass packed into each molecule outweighs the extra space the open lattice creates, so the balance tips the other way. It's further proof that what's floating in your glass is really a balance between a molecule's mass and the space its bonds force it to occupy. That 9% might sound small. It isn't. It's the reason lakes freeze from the top down, not the bottom up. If ice were denser than water, like almost every other frozen solid, it would sink as it formed. Lakes and oceans would freeze solid from the floor upward each winter, with no way for summer heat to reach the deep layers before the next freeze arrived. Instead, ice floats at the surface and acts like a lid. Water beneath it stays close to 4 degrees Celsius all winter, its most stable point. Whole ecosystems spend winter under that lid, in water only a few degrees above freezing. Icebergs formed this way can run 30 to 50 meters thick, taller than a 10-story building, yet still float, buoyed up by that same 9% margin. The same trick scales up to oceans. As sea ice forms, it pushes salt out into the water below. That rejected salt makes the water beneath denser, and it sinks, dragging deep water up to replace it. Oceanographers call this the thermohaline circulation, a slow, planet-wide loop sometimes nicknamed the ocean conveyor belt. moving warm surface water toward the poles and pulling cold, salty, deep water back toward the equator over centuries. Sea ice, forming and rejecting salt near the poles, is one of the engines that keeps that loop turning. 19% quirk in a molecule's geometry insulates every frozen lake on Earth and helps turn the whole ocean over. Here's the part that makes water genuinely strange. Almost nothing else common behaves this way. Chemists count only a small handful of elements that expand rather than shrink when they freeze, among them silicon, gallium, and bismuth, all for a similar reason. Their atoms lock into an open, spaced-out lattice instead of packing tighter. Gallium is a good example. It's a metal that's solid at room temperature, but starts melting in the warmth of your palm. When it cools and re-solidifies, it's doing the same trick water does. Bismuth shows the effect in an even more visible way. Cooled slowly, it grows into colourful, stair-stepped crystals, tinted by a thin oxide layer, a direct result of that same expanding lattice. But none of these are things you handle as a liquid in daily life. Water is the one exception to this rule that you personally touch every day, in your glass, your freezer, and every floating iceberg on the planet. So go back to that ice cube floating in your glass. It looks like nothing, a small block sitting where, by most solids rules, it should have sunk. What's really floating there is a molecule that got cold enough to lock its neighbours at arm's length, instead of pulling them in tight. Nobody designed it that way. It's just what happens when a molecule shaped like a wide V gets cold enough to lock its neighbours into an open frame instead of pulling them in close. Multiply that single quirk by every lake, every glacier, every polar ocean on Earth, and you get a planet where winter doesn't kill everything living in the water, and where the ocean keeps moving, one sinking pocket of salty water at a time. Every floating ice cube is a small rebellion against how solids are supposed to behave, and the planet runs on it. There's another everyday moment hiding in the same kitchen, and it works the opposite way. Not through density this time, but through something else entirely. Pick up a metal spoon and a wooden spoon left on the same counter at the same room temperature and touch them both. The metal one still feels noticeably colder. Even though a thermometer would say they're identical, that's not your imagination, and it isn't really about temperature at all. That's next.